Welcome to the part 5 of a series of videos dedicated to electronic simulation with thermistors and RTDs. My name is Anastas. I'm a product engineer for nonlinear resistors at Vishay. Today we will use different Pspice software in order to compensate a resistive strain gauge in temperature. Let's begin with LTspice, freely available from analog devices at the displayed URL. A strain gauge is modeled as a voltage-dependent resistor. The voltage represents the strain with an equivalence of 1 microvolt equals 1 microstrain. When we sweep the strain voltage from minus 5 mV up to 5 mV, we observe the dependence of the current in function of the strain, but also the unwished dependence in function of the ambient temperature. This effect can be compensated by tuning the bias voltage applied to the gauge with a network of fixed resistors and a thermistor. We will apply this technique directly on a circuit with 4 strain gauges placed in a Wheatstone bridge, which compensate already, naturally but not totally, the temperature changes. As the temperature will increase, the resistance of the NTCS 0603 10 kΩ thermistor will decrease, increasing thus the bias voltage applied to the bridge. In this simulation and for a fixed strain, we will sweep the temperature and compare the variation of the bridge voltage with and without thermistor resistor network. We set up a linear sweep between limit temperatures. All the passive elements, including the NTC, have their electrical tolerances, and here is the simulation result with the green stabilized voltage against the blue non-compensated one. Of course, the fixed resistor values have been optimized in order to achieve this result. The strain voltage is now swept with a variable temperature, and we see thus how the noise in temperature is globally reduced. We will switch now to another software, Symmetrix, from Symmetrix Technologies Limited. The strain gauge Pspice model had to be adapted a bit, but at the end we obtained the same results. Here are the two Wheatstone bridges, with compensation and without. We perform the temperature analysis, and exactly the same results are obtained in Symmetrix as in LTspice. Multisim from National Instruments is next. In Multisim we use the component wizard in order to import the strain gauge and NTC thermistors models. Once again, some adaptations are needed before we can perform the now classical temperature sweep. The result comes as no surprise now. Then comes finally a fourth Pspice software, Pspice from Cadence. If this EDA is your favorite one, once again you won't need to import anything in it because we did it all for you. The syntax differences may be small from one EDA to another. One little bug is enough to induce a simulation stop or failure. That won't be the case here, as all importation processes have been performed as well as the simulations. The result of stabilization is once again confirmed by Pspice. For the case where you would use the version Pspice for TI, we have verified that our simulations work as well in this software. So as a conclusion, we have explored 5 different software, which may have their specificities, but which are always providing a solution, with Vishay Thermistors of course. Well, the part 5 is now over. I hope that you enjoyed this presentation. Thanks for watching.